Welcome to this MOOC course on Foundations of Computational Fluid Dynamics. I just do now course outline for this course. We start off with basic review on fluid mechanics, which includes some important properties and governing equations. Then important topic on Taylor series expansion procedure to obtain different finite difference formula, numerical errors and stability criteria, finite difference formulation for different model equations. Then we go on to finite volume formulation in detail for solving full governing equations, how to do unsteady equations, which means time advancement methods for unsteady flows. Then another important procedure, what is known as a pressure velocity coupling, which is linking momentum equations and continuity equation. All these equations when discretized will result in what is known as linear algebraic equations. Then to solve you have to know different matrix inversion procedure. We will go over that procedures also. Then at the end we will also see a complete demo for 2 or 3 example problem, discretization procedure, how a code is written, how a mesh is set up and what are the results and how to go about writing code, etc. So after going through this course, a student is expected to understand discretization strategies and appreciate different numerical strategies like computational domain, boundary condition, what inversion procedure one has to follow and how to obtain results and interpretation. One also will get confidence on writing a code, because we are going to see at the end a complete working code, details of the code, etc., and that will give you confidence to write own code, or if a code is inherited from some other person or source, then it also requires equivalent skill to understand that code. There are many commercial CFD softwares and open source available. To use them one has to know details, otherwise it will be a wrong selection of choices. So one can understand at the end of this course all the theoretical background based on which the commercial CFD softwares are built. You will also get confidence to apply any CFD code or own commercial software or own code to any engineering application problem. After this is a foundation course. So each of the subtopic is also available in the form of advanced course. For example, grid generation, finite volume method in detail, etc. So one can pursue those higher courses after this course. There are many textbooks available and many online reference material available. So I am listing here particularly 3 or 4 textbook. The student is expected to go through various other materials also. First book on computational fluid mechanics, written by Anderson, Tenehill and Fletcher. Second book, Ferziger and Perrick, book title Computational Methods for Fluid Dynamics. Then there is a book exclusively on finite volume method written by Versteeg and Malala-Shekara. There is a comprehensive textbook on computational fluid dynamics authored by T.J. Chung. As I mentioned before, there are many materials available. So, please do not restrict yourself only to these 4 textbooks. You are also encouraged to read many other online material available to gain confidence on this topic. Now, having described course content, expected outcome and reference textbook, we now move on to the actual course. So, in week 1 I plan to do some important review on basic fluid mechanics, governing equations. We will do a detailed derivation on one or some important term of the derivation, not in detail, they are expected in standard textbook, and some important certain terms. There is some procedure called non-dimensionalization. So, we will go through that and find out why one has to do. There is a specific governing equation, what is known as a vorticity steam function relation. We will do the derivation of that vorticity steam function derivation. Then all these governing equations in fluid mechanics or heat transfer are mostly partial differential equation. You can classify them and we will find out how to classify them based on the solution nature and what is a procedure, how a procedure is different for different types of equation. Then there are different types of boundary conditions available. So, we will go through them also. Then there are different types of problem, we will see those types of problem with example. Then whenever somebody writes a code or set up a numerical strategy to solve any particular problem, there is a procedure called taking a standard test case and proving that code or proving your numerical strategy for the standard test case. So, we will go through few standard test case problems, explain the features in them, what kind of boundary conditions are imposed, and whenever you have to do a code development or using a commercial software, you need to do this first step of proving your code for these test cases. So, this will be the course content for week 1. We now go on to review of basic fluid mechanics. We know we deal with lot of equations or mathematical term. So, we just do what is known as a different coordinate system. So, we know there are basically 3 coordinate system. One is a Cartesian coordinate system x y, second one is a polar coordinate system r theta, third one is a spherical coordinate system which is r theta z. You can convert from any one coordinate system to any other coordinate system, there is a relationship. Now, why do you want to do this? Because all the governing equations need not be only in one coordinate system, you should be able to convert from one coordinate system to other coordinate system and solve problem according to the coordinate system that you can describe for the problem. So, basic quantity, for example, in 2-dimensional coordinate Cartesian coordinate system x and y is related to r theta coordinate system as x is equal to r cos theta and y is equal to r sin theta. So, in cylindrical coordinate system, then we have r is equal to square root of x square plus y squared and theta is related to tan inverse of y over x for x greater than 0 and different relationship for x less than 0. Similarly, spherical coordinate system to Cartesian coordinate system. In spherical coordinate system, you have 3 parameters to define. One is a rho, which is a radius, and theta is angle between 2 sets of coordinate, and phi is angle between another 2 sets of coordinate, and they are related to Cartesian coordinate system x, y, z in this formula that is given here. Rho is equal to square root of r squared plus z squared. So, this is available in any standard textbook or anywhere else. So, we need to know how to convert from one coordinate system to another coordinate system. There are different standard vector operations available. So, we just see what is known as a gradient. If there is a scalar function f, and if you do gradient of f, then you get dou f by dou x I plus dou f by dou y j plus dou f by dou z k. You can also get a gradient expression in other coordinate system r and theta, which is defined as here dou f by dou r, and unit vector in r coordinate system as er. Similarly, for second term and third term. In the same way, you can also define gradient operator in spherical coordinate system, which is given in the last expression. Then another important operation is divergence. So, if you define velocity vector with the component and corresponding unit vector as Vx into I plus Vy into j plus Vz into k, then divergence is defined as del dot V equal to dou Vx by dou x plus dou Vy by dou y plus dou Vz by dou z. Just like we did for gradient, we can also define divergence in other 2 coordinate system, r theta coordinate system and spherical coordinate system. Third important operator is a curl, which is defined as del cross V. So, dou V z by dou y minus dou V y by dou z for I. Similarly, for second component dou Vz by dou Vz by dou x into j, then third component as dou Vy by dou x and dou Vx by dou y for k. So, you can extend this procedure for other 2 coordinate system, and we just define here for r theta coordinate system, as you can see here the first component and second component and third component. Now, these are important because it is easy, or for any quantity later you find them, it is extremely useful. Then another important mathematical related quantity for fluid mechanics is what is known as a total derivative. So, for a function which is defined in x, y, z and t, then one can define total derivative of the function at a point P, and this is defined as capital D of the function by capital D t is dou f by dou t plus dou f by dou x into dou x by dou t plus dou f by dou y into dou y by dou t plus dou f by dou z into dou z by dou t. Now, you can also recognized dou x by dou t is time rate of change of spatial coordinate, which is actually the velocity in x direction. Similarly, dou y by dou t is a velocity component in y direction, so also for velocity component in z direction. Because function f is dependent on 3 coordinate x, y, z and t, we have partial derivative defined for that function in time as well as in other 3 spatial coordinate system. Now, such a derivative is defined here as capital D by dt, which is known as a material derivative or substantial derivative or total derivative. The first term on the right hand side, which is dou f by dou t, is called temporal derivative because it is derivative taken with respect to time. The other 3 terms are called spatial derivative or convective derivative. So, this gives local acceleration and this gives convective acceleration. Now, we restrict ourselves to fluid as a continuum, which means properties are considered to be continuous function of space as well as time. We have just seen a function f function of x, y, z and t, and that is considered to be continuous, the sense there is no gap in between. So, modeling a fluid as a continuum assumes that properties are continuously distributed and fills entire region of the space as it occupies. Now, this assumption does not allow properties to become infinite or to be undefined at a single isolated point. But there are some branches, what is in a molecular dynamics, where there is a question whether this continuum assumption is valid, but in this course we are going to restrict ourselves only to situation where fluid is treated as a continuum. Hence, all the governing equations and whatever procedure we are going to do to deal with those governing equations are restricted only for fluid as a continuum, and it has been tested by several people and several different situations, and this assumption holds good. So, we are restricting ourselves only to a situation where fluid is treated as a continuum mechanism. There is another subject called rarefied gas dynamics, where it is treated not as a continuum. There are many properties. First is a viscosity. So, it is a property by which internal resistance to the fluid flow is defined, and it is just a measure of fluid friction. So, all fluids supposed to have some resistance to the flow, and because of the resistance it develops some stress. Fluid where resistance is assumed to be 0 or no effect is there, such a fluid is called ideal fluid or inviscid fluid. So, in some situation you can assume ideal fluid situation or inviscid calculations can be done to obtain first level of results or approximation. Then that inviscid solution can be taken as a initial condition for subsequent viscous calculation. So, this stage by stage numerical simulation is helpful to overcome any numerical difficulties. There are 2 definitions available. One is absolute or dynamic viscosity, second one kinematic viscosity, it is also called momentum diffusivity, and these 2 are interrelated. So, having defined viscosity stress and strain, one can classify fluid based on how they behave. Okay. So, there is a major classification, Newtonian fluid or non-Newtonian fluid. In Newtonian fluid, there is a linear relationship between applied stress and resulting rate of deformation. In non-Newtonian fluid, there is a nonlinear relationship between the value of the applied stress and the rate of deformation. So, there is a graph available. So, on y axis you have the stress tau, and x axis you have the rate of strain d by dt of epsilon, which is strain. So, A is a linear straight line, it is a linear relationship between applied stress and the resultant strain. That behavior, which is marked here as A, is known as a Newtonian fluid. Any other behavior which is marked in this figure, either B, situation D or situation C, where the linear relationship is not followed, they are called non-Newtonian fluid. So, we have example, toothpaste is example for non-Newtonian fluid, blood is example for non-Newtonian fluid, grease is example for non-Newtonian fluid. So, whenever you have a non-Newtonian fluid, there are different models available to describe them. The popularly used is a power law model, where the stress is related to rate of deformation by power law. So, it is d by dt of strain to the power of n, the n is the index of the power, and you can separate as d by dt of delta to the power of n minus 1, and the remaining one part is written separately. This product k into d delta by dt to the power of n minus 1, this term alone is referred as apparent viscosity, which is written by the symbol eta. So, d by dt of remaining term delta, and which is related to strain du by dy, this is velocity strain. Okay. So, this is because in general for Newtonian fluid we write tau equal to mu into dou u by dou y or du by dy. So, for non-Newtonian fluid also we would like to have a similar expression, and that is written here as eta into du by dy. The difference here is eta is apparent viscosity, mu is another viscosity. So, we can go one more small sub classification, fluids where apparent viscosity, which is eta, decreases with the increasing deformation rate, which means n is less than 1, is called pseudoplastic, which is marked here as C in this curve. So, the relationship between stress and rate of strain, it is decreasing with increasing. So, on x axis as you go it increases, whereas the rate here is smaller on the other axis. The second situation, if the apparent viscosity increases with the increase in deformation rate, which happens for situation marked as D here, and that is what is known as a shear thickening fluid or dilatant fluid, which is marked here as D. So, there are situations where there is a stress required, then the fluid will start moving. So, that is the meaning of situation where B. So, they will not start flowing up to some definite pressure is set from plastics. We also now go to the next topic, what is known as a scalar or vector fields, because in fluid mechanics we talk about velocity, temperature or concentration. So, we should know what is a scalar field and what is a vector field. So, a field is a quantity which can be defined as a function of position at every point in space. This may be a scalar which has only the magnitude, or vector which has both magnitude as well as direction. When a scalar quantity is defined as a function of position, then it is said to be scalar field. Similarly, when a vector quantity is specified at every point as a function of position, then it is said to be vector field. So, for example, temperature is a function of x, y, z, and if you prescribe temperature, then it becomes scalar field. Similarly, vector velocity is defined, then it becomes velocity field. Because it is direction dependent, you can also take a component. So, component of vector field are called a scalar field function. So, just like velocity vector v, if you take a component in x, y, z, then we get corresponding component of velocity in the direction. Though it is defined as a scalar field, it keeps on changing. So, even if you take only the velocity component, as it keeps on changing in x direction, for example, then the direction along which the change happens results a vector. So, for a flow field, velocity vector v, which is a function of spatial coordinate x, y, z, also as a function of time, you have a 3 component u, v, w, and all 3 also varies as a function of x, y, z as well as time. And to get back to the velocity field, vector field, you multiply the magnitude with the corresponding unit vector I, j, k. So, one can obtain from the scalar field vector field in this way. Next quantity of interest is vorticity vector, and omega is a symbol used to define this vorticity vector. Expression for omega is shown here with its component. So, omega equal to omega x into I plus omega y into j plus omega z into k, and that is also equal to half times del cross v, where v is a velocity vector, and that is equal to half rotation vector, which is capital omega. And in terms of detailed Cartesian component, rotation is given here as dou w by dou y minus dou v by dou z into I. This is the x component. Similarly, expression for y component, dou u by dou z minus dou w by dou x into j, plus expression for third component, dou v by dou x minus dou u by dou y into k. Expression for cylindrical coordinate system is also given here. Now, we know in a fluid particle is subjected to body force or normal force as well as shear force. A fluid particle moving without rotation in a flow field cannot develop rotation under the action of body force or normal force. Development of rotation in a fluid particle initially without rotation requires action of shear stress on the surface of the particle. If the rotation or vorticity is 0, that is del cross V is 0, such a flow is called irrotational flow. Since the shear stress is proportional to the rate of angular deformation, then a particle without initial rotation will not develop rotation without any simultaneous angular deformation. So, for a fluid to have rotational viscous force which actually results in the form of a shear stress is responsible for rotation. In this first module I outline syllabus for the entire course, outcome of this course, what is expected from this course, reference textbook, important fluid properties, basic review on mathematical operations, viscosity and something about rotation. So, next class we are going to continue this and slowly move on to governing equations. Thank you.